Okay, so okay, so this is officially called a neutralization reaction. All neutralization reactions, no exception, produces water and a salt. What happens is the proton on the acid, the hydroxyl ion on the base combine, and that's where the water comes in. And what's left over is the salt. So what's nice about this, because this happens in its solution, so we're talking about a water solution here. This can be used advantageously to determine unknown concentrations of either an acid or a base. Now, your lab, that 2-week lab we're going to be doing next week, the first part of the lab is to determine the concentration of our sodium hydroxide. And what we're using a not hydrochloric acid, we're using a solid acid. It's called KHP. And if the P is not phosphorus, by the way, the P stands for phthalic acid. So you just need, in your write-up, it'll give you the formula for it, so, because you need the molar mass. So what we're going to do is, we know the concentration of this and the volume of this, we can find the moles. If we know the concentration of this and the volume of this, we can find moles. Now, as far as Chem A is concerned, not Chem 1A or 2A, Chem A is okay, so 1 mole of acid neutralizes 1 mole of base, or vice versa. Now, why I specified in Chem A is we're only going to be using monoprotic acids. Remember, there's diprotic acids like sulfuric acid that has 2 protons. In that case, you would have 1 mole of diprotic acid neutralizes 2 moles of base. So the calculations are slightly different. Okay, but as far as we're concerned, 1 mole of acid, 1 mole of base, boom, neutralizes each other. Okay, at that point, it's called the equivalence. The equivalence point, when it's exactly even. Now, at the equivalence point, this is then true. Bless you. Okay, now the problem is, how do you know that you're at this neutralization point? Well, there's a couple ways to do this. One is a meter that measures pH. At the equivalence point, for most common acids we're running into in Chem A, 1A, 2A, 3A, we're going to use something called an indicator. And the indicator will tell us the equivalence point has been met. And in indicator jargon, that's called an endpoint. Now, all chemistry classes at this school anyway does titrations. Not so at Sac City. Only the 1A classes and the 1B classes do titrations, except for my class. I made an assumption that the prior class to 2B, which was 2A, did titrations. That's true here, but not at Sac City. So my poor students, I assumed they knew how to titrate, and they didn't. So anyway, we use indicators. Indicators are just a chemical that will change color when the equivalence point is met. Now you're going to be using a really cool indicator. It's been used for probably a century and a half. It's called phenolphthalein. It's kind of a mouthful, but it's so cool. So what it does, when it reaches the equivalence points, it turns this really pretty pink. I call it Barbie pink. It's very cool color. And what you do is you keep dropping the base in until this neutralizes. At that point, the indicator turns pink. So then you stop. Now you know how much base you used, you know the concentration of the base, you know how much volume of acid you have in there, and you know the concentration of the acid. So that's what we're going to do next week. So the first part of the lab is to determine our concentration of the base. So, for example, let's get rid of this. Oh, and there's and this equivalence point, when it's neutralized, the pH is equal to 7. So the other way to determine the equivalence point is with a pH meter. pH meters are expensive though, so that's why we use indicators. So this is a couple $100 instrument times how many lab stations we have in the lab, cost a lot, as opposed to 3 drops of this indicator. So that's why they use the indicator. Okay. So let me diagram what the setup is. Okay, you're gonna have a long tube about this high with a valve at the bottom, and it's calibrated in milliliters. And that is called a burette, or some of my students pronounce it beret. And its purpose is to deliver a certain volume of liquid. Now, in the case of our lab, that liquid is going to be sodium hydroxide. So it starts at 0 and goes down to, I forgot whether it's a 25 or 50 milliliter burette, but let's just say it's 25. So as the liquid goes down, you can measure how much liquid has been dropped out of that burette. So where does it go? It goes into a beaker with acid in it. That's the indicator. Okay, so we have a volume of base, and we know we need to calculate the concentration of the base. Because remember, there are 4 parts to this: base, concentration, and volume, acid, concentration, and volume. So there's 4 parts. You're gonna know 3, and then you calculate the 4th one. Okay, so we're going to put a known volume of acid in there, like I think it's 20 mils. And then we don't know the concentration. Up here, we know the concentration. Let's say it's 0.1 molar. And then when we go drop, 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 and it turns pink, we stop. Now we know the volume in milliliters. Okay, so normally with titrations, we want to calculate concentration of the unknown acid concentration. Okay, that'll be the second part of your lab coming up. Okay, in fact, you're going to be titrating vitamin C tablets. So you want to know the concentration of the vitamin C tablets. Okay, and you put a known amount concentration, a known volume of the acid in there. So we have volume, unknown concentration. We're going to take and neutralize that with this sodium hydroxide up in the burette. So we know volume, the volume comes from the burette reading as it drops down into the acid indicator. And we know the concentration of sodium hydroxide. So this is the essence of the calculation. Okay. At the equivalence point, the moles of acid equals moles of base. Now, yesterday we talked about getting moles. Moles is concentration times volume equals moles. Concentration times volume equals moles. So there is that equation that we talked about yesterday. So remember when we did the dilution, we had moles of concentrate equal moles of diluted. Same thing. So concentration of the acid, volume of the acid, concentration of the base, concentration or volume of the base. So now we're going to do A's and B's. Okay, so at the equivalence point, we know the volume of the base. We need to convert the milliliters to liters, though. So first thing is, and we know the concentration of the base from this value up here. Concentration is 0.1 molar. The volume is going to be read off the burette. So that's going to be and then the milliliters from the burette. Now we need to convert the milliliters to liters, though. So that's going to be that conversion, because it's got to be in liters, because concentration is in moles per liter, not moles per milliliter. Okay, so, and again, the idea is to calculate the concentration of the acid. So we don't know M sub A. We do know the volume, 20 milliliters, converted to liters. Now we just solve for M sub A. Now notice something here. Those conversion factors cancel. So that automatically leaves you with 2 less calculations to do. Okay, so this calculation will give you the concentration of the unknown acid. So basically, we're going to divide .1 by 20. So the concentration of the acid is 0.005. And of course, we need to do sig figs, so it's going to be, what, two sig figs. Okay, so this is really important. Now, you're going to have a titration question on your test 5. So remember, there are 4 parts to a titration question. The base parts and the acid parts. And you have to have 3 of the 4 to calculate anything else. So frequently, let me show you what a titration problem is going to look like. Okay. So 20 mils of an unknown acid is titrated. Now, when I say titrated, that's the burette, the acid base setup with the indicator. That's what titration means. Now, that term is used a lot in medicine. For example, when you go and get an allergy series of tests to determine what you're allergic to, that's called a titer, T-I-T-E-R, and it's a titration. It's a titration. So it's used a lot in the medical field. This is an this is an acid-base titration, but there are also oxidation reductions titrations. There are all kinds of titrations. A titration is a generic term to determine an unknown by putting something known against it. Okay, so remember, we need 3 of the 4 on all titrations. Okay, so we've got volume of the acid, that's one of them. We've got the concentration of the base, and after we subtract these 2, we'll have the volume of the base. So we've got 3 parts of the 4. Okay, so the first thing is find out how much volume was used to neutralize the acid below. Okay, you do that by subtracting the final volume from the initial volume. Now, many people like to start at 0 on the top of the burette. You don't have to. It makes this subtraction trivial. Okay, but you don't have to. Some people don't. They just, whatever the volume is you start with, they don't care. They just, that's what it is. And then when they finish at the equivalence point, the end point with the indicator, they just subtract the two. So in this case, I'm not going to start at 0, but you can easily start at 0. And it's got to be 0.00. Okay, that means you got to estimate between the lines. Okay, and I'm not going to do this in my head. Okay, so we're talking about okay, so 21.11 milliliters of base. So going back to our at the equivalence point, 1 mole of acid equals 1 mole of base. I'm going to convert it to concentration of acid times the volume of acid equals concentration of base times volume of base. So those are the 4 parts, and we've got all except for the concentration of the acid right here. Okay, so the volume of the acid is going to be 20 milliliters. Times the concentration of the base, which is 134, times the 21.11 milliliters. So this is the base, and this is the volume of the acid. So what we're going to do now is we're going to solve for M sub A. Okay, and these guys are just to convert the milliliters to liters. Okay, and those again are going to cancel. So really all we're doing is we're multiplying 134 times 2111 divided by 20. Okay, so it's 141 moles per liter. That is a very, very generic and common titration problem. Now, the lab we're going to do on next week is called a standardization lab. It's also titration. We've got to find out the concentration of the base, the sodium hydroxide. To do that, we're going to do this in reverse. We know the concentration of the acid, or the volume of the acid. So we're going to do this in reverse to find out the concentration of the base instead of the acid. And then once we find that out, you're going to store that in the big cart for the following week. Do not dispose of that, because you're going to have to do the whole thing again. Okay, so the purpose of next week is to determine the concentration of the base. And then the following week, we're going to use that base that we've standardized, figured out what the concentration is, to figure out our unknown acid concentration, the vitamin C. Now, it was very important for me to do this today and yesterday, because going into Friday without this information, it would be totally unknown. Okay? All right. Did everyone follow this okay? It seemed reasonable? Okay. All right. Now, today's lecture was to focus on this. Okay. So you want me to do another problem? Just, okay. Okay, so let's change this to, let's say, 15 milliliters. And this time I'm going to start at 0. Okay. So same thing now. And I'm going to stress, this is after the indicator turns pink. Up until that time, nothing is valid, because the indicator tells us the equivalence points has been met. And this is true only at the equivalence point, only when the indicator tells you so. And the indicator will turn pink, and as soon as it turns light pink, stop it dripping, the burette. Don't continue going on. The darker the pink, the farther from the end point you've gone. So again, we have okay, so the concentration of acid is unknown. Well, the volume of the acid is 15 milliliters. And then we have to convert it to liters. Concentration of the base is and we're looking at 13. Okay, so in this prior problem, I had to do this subtraction. Because we started at 0, you don't have to do the subtraction. That's why everyone likes to start at 0. But it's a pain to get it exactly at 0. You got to use your dropper, and I just say it doesn't matter. Just so for me, I've been used to doing this for decades, and I just anyway. Okay, so then we need to convert this to liters. Okay. Then we just solve for the concentration of the acid. Okay, and again, these guys cancel. So it's the same thing each time. The only difference is next week, instead of a liquid acid, we're going to be using a solid powder acid. And so you're going to be using the moles of that. It's going to be the molar mass of it. You have to calculate the molar mass, convert that to grams. Convert the grams to moles. Okay, so any questions about this process? And when you read through your lab, it'll explain this again, probably differently, slightly differently than I did it. But the concept is exactly the same. Mole of acid, mole of base equal at the equivalence point. Only at the equivalence point. And frequently, labs will not talk about equivalence points, they'll talk about endpoints. And when you choose an indicator, there are hundreds of indicators out there, all these different colors. And you have to choose the endpoint of the indicator to match your equivalence point. Because if they're not the same, you're not going to get accurate results. So you want to choose your indicator's endpoint to be the same as the equivalence point of your reaction. And that's what we're using phenolphthalein for, because that's what it does. So it changes color at around 7. That's when you have neutrality between the acid and the base. Okay. Now, this, in some ways, is the basis for, now there's a lot to acids and bases. A lot. In this class, they wanted me to focus on the concept of neutrality when you mix an acid and a base. What is an acid? What is a base? That kind of stuff. And then getting into titration. Now, there's a whole bunch of other stuff about acids and bases. And by the way, this calculation gets very complex when we're working with weak acids and weak bases. Very complex. End up with solving a quadratic equation and all this other stuff. But if we keep it to strong acids and strong bases, it's very straightforward. As straightforward as this can be. Okay. So I'm going to get back to solutions now. Now, acids and bases are 99.999% in a water solution, except sometimes in a biochemical environment, they're not in a water solution. But most of the time, they're water-based. Okay, so before I leave the screen, are there any questions about this guy? Okay. All right. So what I'm going to do is I'm going to do a little bit more on this concept of solutions. What I'm going to do is we're going to take 2 solutions and dump them together. Each solution's at a different concentration than the other one. So when we dump them together, there's going to be a new concentration. Okay, you have to remember though, again, we have concentration times volume. So that's concentration, volume again, equals mole. Okay, so let's all right, so we got a 5-liter solution of sodium chloride and a 2-liter solution of, and we're going to dump them together. So okay, there are different concentrations. I'm going to dump those together. So to calculate concentration, we need moles and liters. Moles per liter. Okay. What's our new volume? 5 plus 2. Right. 7 liters is our new volume. Let's say that's the easy part. What's our new moles? Well, we have to calculate moles of each one, add them together, and that's what's going to go on here. Okay. So we have okay, that'll gets us moles of sodium chloride. Okay, here it's going to be 375 and 2 liters. Okay. So again, concentration times volume equals moles. Concentration times volume, concentration times volume. Moles of this plus moles of that goes up here. So we end up with moles per liter. So the new concentration is 0.232 moles per liter. So there's 2 calculations here. What's the final volume? What's the total number of moles? So we have to calculate moles here, add them together, and that's what's going to go up here. Now you're going to have one of these on your test 5 also. So are there any questions about how we ended up with this? Now this is almost as tricky as it's going to get in here. There's one little nuance involving acids and bases that I'm not going to do today. But basically what we're going to do is we're going to take a solution, I'm going to of sodium hydroxide and dump it into an acid. I'm going to figure out what the final concentration is, whether it's acidic or basic, and what that concentration is. That's a little more complicated than this, but the concept is the same though. We have do the volume first, then you do moles of acid, moles of base. One's going to cancel the other out and you have something left over. Okay, so does this make sense, this guy? All right. Believe it or not, we're sort of finished with the unit 5, except for that one problem I'm going to do on Friday. Other than that, we're basically done with unit 5. So what I'm going to do starting Friday after I talk about that acid base problem is going to be review unit 5 problems. Okay. All right. So let me do one more of these and that'll be it for today. Okay, so okay. So what I like to do is the simple calculation first, which is what's our new volume? We have 3 and 5 liters. What's our new volume going to be? And then we calculate the new numbers of moles. Okay, so we've got okay, so now we have 8.77 liters. Now we need to do moles of each one. So that's 1.51 I added, I mean, the 576. I just invented it. I can't believe I did that. Let's do this again. 476. Depend on my students to keep me straight. Okay. So that's going to be it for today. And I invite anyone who'd like to stay after. We can go over problems if you like, or you can go. All right. Any questions about anything so far? Okay.